Hello everyone, my name is Yuan Zhou. Today I will present our work titled Distilling Arbitration Logic from Traces Using Machine Learning, a case study on NoC. This is a joint work with Yuan, Professor Jiming Yin from Lehigh University, and my advisor, Professor Zhou from Cornell University. Designing an effective arbitration policy has been a challenging task in computer systems, and is becoming more challenging nowadays. With modern computer systems becoming increasingly complex, it is more and more difficult for humans to design and optimize sophisticated arbitration strategies that can satisfy the performance constraints. As a result, automatically learning arbitration policy using machine learning seems to be a promising direction. Simulation traces is an ideal source of data in this case, because they are abundant, contain a lot of information about the target problem, and are suitable for machine learning models to process. Here I am showing an example of NoC packet arbitration. With a sufficient amount of data from the traces, it is straightforward to train a multi-layer perceptron, or MLP, to solve this problem. However, a critical challenge is, how do we implement these models in hardware and satisfy the design constraints? In hardware, the latency constraints to make decisions are usually tight, and the area budget of the arbitration logic is limited. For the NoC arbitration problem, a typical router needs to make the decision within 1 to 2 cycles, and the area of a simple router is around 4,500 micrometers squared. A full-fledged accelerator cannot possibly hit the latency target. Another solution is to use an array of multipliers and insert a few stages of registers. For this solution, the arbitration logic will consume too much area compared with the area of the whole router. The third solution, which is common in existing works, try to manually convert the trained deep learning model into implementable logic. The downside of such approaches is that they require a lot of domain knowledge and cannot really scale to large models because manually analyzing large deep learning models is generally infeasible. To tackle this challenge, we propose circuit distillation, which to the best of our knowledge is the first systematic approach to automatically derive efficient arbitration logic from simulation traces. The figure on the right shows the overall flow of our approach. The key idea is that we train deep learning models from simulation traces and then use tree-based models as a bridge to convert deep learning models to combinational logic. We present a case study on NoC arbitration in this work, where our circuit distillation approach shows promising results. The generated arbitration logic achieves 2 orders of magnitude performance improvement compared with the baseline policy on the training traffic, only uses area comparable to 3 8-bit adders, and generalizes to another traffic pattern which is unseen during training. Before we dive into the details of our technique, let me first introduce some background on reinforcement learning and tree-based models. In reinforcement learning, an agent learns its decision-making policy by repeatedly interacting with the environment and learning from its experiences. At time step t, the agent gets the current state from the environment, makes a decision based on its current policy, and performs an action that affects the environment. The state of the environment gets updated by this action, and the environment will provide a reward, usually a scalar, to the agent. The current and next states, reward, and the action are used to update the agent. There is a lot of freedom for the user to customize the learning process. For example, the user can choose how to represent the state, what are the possible actions, how to design the reward function, how to represent the policy, and how to update the policy. We only consider tree-based models with a single tree. We are not considering random forest or gradient-boosted trees because of area concerns. They have many trees and thus are more expensive to implement in hardware. Here I am showing simple examples for decision tree and model tree. The major difference is that decision trees have constants as leaves and learn step functions, while model trees have models instead of constants at leaves. This particular example has linear models at the leaves, so it's called a linear model tree, and can learn piecewise linear functions. Starting from a trained DNN model, the first step of our circuit distillation methodology is to train a tree-based model from the DNN model. There are two ways of collecting training samples from the tree-based model. One is to sweep all possible input combinations of the DNN model. The other one is to collect training samples from simulation. While the first method allows the tree-based model to learn from a complete representation of the DNN model, the second method is more scalable and maintains the sample frequency information in the real use case. Before training the tree model, the inputs and the outputs of the DNN models must be rescaled to simplify the hardware implementation. After we get the tree model, we can regularize and quantize it to make it more area efficient. We can regularize the tree models by constraining the maximum tree depth or quantize the weights of linear model trees. In this work, we use power of two quantization to completely eliminate multiplications and simplify the hardware as much as possible. Both regularization and quantization control the trade-off between accuracy and area. Implementing the trees in hardware is pretty straightforward. Both decision trees and linear model trees can be implemented using an array of multiplexers and comparators. For linear model tree, we are also showing the power of two quantization, where the multiplications are implemented as shifts in the end. Our case study is a network-on-chip packet arbitration task. As shown in this figure, the goal is to select one from the packets competing for an output port. We compare our approach with three commonly seen baseline policies: round-robin, FIFO, and a global age-based Oracle policy. Our experiments are performed in Gen 5 on a 4x4 mesh network, and our setup is similar to a prior work in last year's HPCA conference. This slide shows the architecture of our switch allocator. Each virtual channel has an arbiter that computes a priority score, and the packet with the highest score will be selected. We use local age, payload size, hop count, and distance as features to the arbiter. Notice that these features are also used in the HPCA paper I mentioned earlier. During training, we use a multi-layer perceptron to replace the arbiter. All the multi-layer perceptrons share the same weights. We train our agent with uniform random traffic under an injection rate that is close to the Oracle policy's saturation point. Our MLP agent is trained using deep Q learning, and a reward of 1 is given only if the MLP agent makes the same decision as the Oracle policy. The figure on the right shows how the average packet latency of our agent improves during training. It quickly got much better than the baselines and gradually approached the Oracle policy. Let's take a look at the performance of the learned arbitration logic. On the left side, I am showing the area and performance comparison of different arbitration policies under uniform random traffic. Notice that this is also the training traffic of our reinforcement learning agent. Rows colored in orange show the area and performance of logic distilled from decision trees. The next 5 rows show the logic distilled from linear model trees, while the rows in yellow are the 3 baselines. As we can see, the logic distilled from tree-based models significantly outperform the FIFO policy and the manual policy from a prior work. In addition, linear model trees generally perform better than decision trees on this task. I would like to invite you to focus on the highlighted rows. The linear model tree with a max depth of 4 achieves the best average packet latency among all the learned policies, while the linear model tree with a max depth of 1 achieves an attractive trade-off between performance and area. Notice that the area of an 8-bit combinational adder is around 17 micrometers squared under our target technology node and frequency. So the area of this arbitration logic is less than 3 8-bit adders. The figure on the right shows how the learned policy generalizes to different injection rates. As we can see, the learned policy is able to generalize well to all injection rates and achieve comparable performance with both the original MLP agent and the Oracle policy. Another benefit of using tree-based models is that we can actually look at the policy and figure out what it is doing. Here I am showing the policy learned by the linear model tree of depth 1. As a comparison, here is the manual policy mentioned in the previous slide. Compared with the manual policy, our policy handles packets with long and short routes differently. Also, it places much less emphasis on local age, so that it does not quickly degenerate to the FIFO policy under heavy traffic. Finally, our policy focuses more on topology information. Finally, let's see how the learned policy generalizes to a different traffic pattern. This figure shows how the agents trained under uniform random traffic generalizes to the transpose traffic, where node XY only communicates with node YX. The MLP agent and the linear model tree with depth of 4 generalize pretty well. The linear model tree with depth of 1 performs slightly worse, but recall from previous slides that it is much more area efficient than the other two learned policies. All the learned agents outperform the round-robin FIFO baselines by a large margin. To make sure the agent can generalize well to different traffic patterns, in practice, we should try to include more traffic patterns into the training traffic. To conclude, in this work, we have shown that we can effectively distill arbitration logic directly from simulation traces using a combination of reinforcement learning and tree-based models. Our case study on NoC arbitration shows that the proposed approach can achieve good area performance trade-off. For future work, we plan to enrich our case study by experimenting on more realistic workloads and traffic patterns, and generalize our approach to other problems in computer systems. A long-term decision is to investigate how to generate efficient sequential circuits from stateful machine learning models, which would enable us to solve a wider range of problems in computer architecture. That's all of my talk. Thank you for your attention.